What if I told you that ancient Rome routinely built faster than we do today? Not just faster in a poetic sense, but measurably faster in ways that would shock modern engineers, planners, and policymakers. They did it without electricity, without engines, without computer simulations, and without the layers of bureaucracy we now consider inseparable from large-scale construction. In just 10 days, Julius Caesar's legions constructed a massive timber bridge across the Rhine River, wide and strong enough to move an entire army. Today, a comparable bridge would spend years in feasibility studies, environmental impact assessments, procurement negotiations, and public hearings before a single foundation pile touched the riverbed. The Colosseum, a structure so large it still defines the Rome skyline, seating up to 80,000 people and incorporating complex crowd control, drainage, and structural systems, was completed in roughly 8 years. Modern stadiums, often smaller, lighter, and built with vastly more powerful machinery, frequently struggle to meet 5-year construction timelines once ground is broken. So how did the Romans achieve this level of speed? How did an ancient civilization consistently execute mega-projects at a pace that feels almost impossible today? Stay with me until the end, because the real answer isn't a single tool or material. It's a hidden construction system the Romans mastered, and one we've quietly abandoned. The first foundation of Roman speed was not technological in the modern sense. It was conceptual. The Romans understood standardization at a level no civilization before them had attempted. Where other ancient cultures treated architecture as bespoke art, each temple, palace, or monument designed as a singular expression, the Romans treated building as an industrial process. Measurements were standardized across the empire. Units like the Roman foot, palm, and pace were enforced consistently. Brick sizes were regulated. Stone blocks were cut to known dimensions. Arch ratios, column proportions, and road widths followed repeatable formulas. This meant that an engineer arriving in a distant province did not start from scratch. He worked from an inherited system of assumptions, proportions, and methods that had already been tested across the empire. A brick fired in Gaul could be shipped to Syria and fit perfectly into a wall designed thousands of kilometers away. Supply chains became flexible instead of fragile. If one quarry slowed down, another could step in without redesign. Construction no longer waited on artisans producing custom elements. It flowed continuously. Even contracts were standardized, with legal frameworks specifying materials, timelines, and penalties, transforming construction from an uncertain craft into a predictable administrative process. In this sense, Rome did not merely build structures, it built a construction bureaucracy that scaled with empire. But materials and rules alone do not raise walls. Labor does. And Rome's labor force was unlike anything the ancient world had seen. The Roman legionary was not simply a soldier, he was a trained builder by necessity. From the moment of enlistment, recruits learned how to dig trenches, fell trees, erect palisades, lay stone, and follow precise geometric layouts. Engineering discipline was inseparable from military discipline. Each legion included specialists, surveyors, engineers, carpenters, blacksmiths, men exempt from routine guard duty so they could focus entirely on construction. This turned every legion into a self-contained infrastructure unit. On the march, armies did not sleep in improvised camps. Every single night, regardless of weather or fatigue, legions constructed a fully fortified camp with straight streets, drainage, gates, and defenses, often in as little as 3 to 6 hours. This repeated daily ritual ingrained construction efficiency into muscle memory. When the army arrived at a river, a bridge appeared. When it reached a frontier, a road followed. Rome did not conquer land and later decide how to hold it. Infrastructure was the mechanism of conquest itself. At the heart of Roman construction lay a material that modern engineers long misunderstood: Roman concrete. Known as opus caementicium, it was not simply an early version of modern cement, but a fundamentally different chemical system. Its key ingredient, volcanic ash known as pozzolana, reacted with lime and water to form stable crystalline structures. Unlike modern Portland cement, which is strong early but chemically brittle over time, Roman concrete gained strength slowly and continuously. In marine environments, where modern concrete often fails catastrophically, Roman concrete improved. When seawater penetrated the material, it triggered reactions that formed minerals like tobermorite, reinforcing the structure from within. Even more remarkable is what modern researchers discovered only recently. Romans practiced what is now called hot mixing. By adding quicklime directly into the mix, they caused intense heat reactions that created tiny lime clasts, small reactive pockets embedded throughout the concrete. When cracks formed and water entered, these clasts dissolved and recrystallized as calcium carbonate, sealing the cracks automatically. Roman concrete was not just durable, it was self-healing. This reduced maintenance demands dramatically. Structures did not need constant repair, freeing labor and resources for new construction. Time, in effect, became an ally rather than an enemy. Roman roads illustrate how this philosophy translated into infrastructure. These were not simple stone paths laid on soil. Road construction began with deep excavation until solid ground was reached. Layers followed in precise order: large foundation stones for stability, compacted rubble mixed with lime, a finer concrete layer, and finally tightly fitted paving stones cut so precisely that a knife blade could not fit between them. Roads were crowned to shed water, with drainage ditches on either side preventing erosion. This obsessive attention to structure meant Roman roads required virtually no resurfacing. Their maintenance cycle, in modern terms, was measured in centuries. Many modern highways still follow Roman alignments, not out of nostalgia, but because the Romans had already chosen the optimal routes and built them on stable foundations. When compared to modern roads that require constant patching and periodic reconstruction, Roman roads were astonishingly efficient over time. The scale of Roman construction raises an obvious question. How did they move such enormous quantities of material without engines? The answer lies in mechanical intelligence. Roman engineers mastered mechanical advantage. The treadwheel crane allowed 1 or 2 workers to lift loads that would otherwise require dozens of men. By walking inside a large wheel, human weight was converted into rotational force with remarkable efficiency. For heavier loads, multiple cranes were synchronized using pulley systems, capstans, and winches. Complex lifting operations became routine. Massive stone blocks weighing tens or even hundreds of tons were raised into position with precision. Construction was also modular. Seating blocks, stair units, and architectural components were often prepared separately and installed as units. Large buildings like the Colosseum were not slowly carved into existence, they were assembled from standardized parts. This modularity compressed timelines dramatically. Roman expertise extended beyond visible structures into systems that shaped daily life. Aqueducts are the most famous example. While monumental bridges like the Pont du Gard dominate the imagination, Most Roman aqueducts were hidden underground. This protected water supplies from contamination and sabotage. Gradients were extraordinarily precise, often descending only a few centimeters per kilometer. Roman engineers achieved this using simple but effective surveying tools, water levels, sighting instruments, and straight-line markers. When valleys interrupted a route, they used inverted siphons, forcing water down and back up using pressure alone. Channels were lined with waterproof mortars made from crushed ceramics and lime, preventing leakage. The result was a reliable water supply that transformed settlements into cities almost overnight. Baths, fountains, sewers, and irrigation systems followed, binding populations to Roman authority through comfort and convenience rather than force alone. Given all this, it's tempting to conclude that modern society has somehow regressed, but the reality is more complicated. Modern construction is slowed not only by inefficiency, but by choice. Regulatory frameworks, safety standards, environmental protections, and public accountability all add time. Permits that once took months now take years. Environmental impact studies alone can consume entire project lifespans. Modern buildings are also vastly more complex internally, requiring electrical grids, climate systems, data infrastructure, and compliance with safety codes unknown to antiquity. At the same time, we suffer from survivorship bias. We see the Pantheon and assume Roman construction was flawless. We forget the countless cheaply built apartment blocks that collapsed or burned. Speed in Rome often came at a terrible human cost. The collapse of the amphitheater at Fidenae in 27 AD, which killed tens of thousands, stands as a grim reminder that rapid construction could be deadly. Roman developers, driven by profit, frequently cut corners, especially in housing for the poor. And this brings us to the true secret behind Rome's speed. It was not a single material or machine, it was systems integration. Rome synchronized standardized materials, disciplined labor, legal frameworks, logistics, and ideology into a single construction engine. Most crucially, they used permanent formwork. Their brick and stone facings were not decorative shells added after the fact. They were structural skins built first, forming a rigid framework into which concrete was poured. These facings carried loads early, allowing construction to continue without waiting weeks or months for concrete to reach full strength. Concrete cured slowly inside, sometimes over decades, gaining strength as time passed. The Romans did not build for short-term return on investment. They built for permanence, for symbolism, for domination through durability. Their structures were designed to outlast generations, even centuries, and in many cases, they succeeded. Rome's construction speed was not magic. It was the product of a civilization that treated building as an extension of power, organization, and worldview. They did not ask whether something could be built quickly. They designed their entire society around making it inevitable. So the real question is not whether we could build like the Romans again, but whether we would choose to. Should we revive self-healing materials that reduce long-term maintenance? Should we rethink how standardized systems can accelerate infrastructure without sacrificing safety? Or should the lessons of Rome serve as a warning about what speed can cost when human life becomes expendable? The ruins still standing across Europe and the Mediterranean do not just tell a story of ancient engineering. They tell a story about priorities and about what happens when an empire decides that building itself is an act of conquest.